Hello and welcome to a video about energy as part of your second topic in stage 1 physics, energy and momentum. In stage 1 physics, you'll learn that the work done on an object is equivalent to the change in energy of that object. And when a force is applied to an object causing displacement over a distance, work is done. The expectation is that you'll be able to explain work in terms of an applied force and that you'll be able to solve problems using these two equations here. So work equals change in energy as well as work equals force times displacement, where the displacement is parallel to the force. So we'll start off with some definitions. First of all, energy, and this is the ability to do something or to cause change. The unit for energy is joule. You might have heard of this in terms of food, like how many joules or kilojoules are in a given food item. Usually it's on the back of a packet with that table with all the different nutrients like sodium, sugars, etc. Energy is scalar, so it doesn't have any direction and it can be neither created nor destroyed. It is, however, transformed or transferred. So you can't create energy out of thin air, but you can transfer it between objects or you can transform it into a different form of energy. Energy is transferred between objects via work, and work is done when a force acts on an object and causes energy to be transformed or transferred. So it's a measure of the change in energy. That's why we've got this rule here indicating that work is a change in energy. Because energy is measured in joules, the change of energy or work is also going to be measured in joules. Work is done when an applied force causes an object's position to change. So work is also equal to force times displacement. Obviously it's also it's work, so it's going to be, the units are going to be joules. You can see that joules, or hopefully you can see that joules are equivalent to Newton meters because force is measured in newtons and displacement is measured in meters. So that must mean that if work is equivalent to a change in energy, it's measured in joules, and if work is also equivalent to force times displacement, then the units must also be Newton meters, therefore joules must be equivalent to Newton meters. When we're measuring work using the force and displacement, we only include the force that's acting parallel to displacement. So if you have, just say we've got, some random object here and it's travelling in this direction, but the string that's pulling it along is at an angle to the horizontal, we have to resolve the tension force vector into its horizontal and vertical components. So with that, we'll do an example. A box is pushed along the ground for 15 metres with a force of 30 newtons. How much work is done? So it's handy to draw a vector diagram so you can visualise what's going on. There's a box, there's the ground. It's being pushed for 15 metres and the force, just say, is acting to the right and it's 30 newtons. So we know that work is equal to force times displacement. The force is 30 newtons, the displacement is 15 metres. Therefore, the work that is being done must be 450 joules or 450 Newton meters. So that's hopefully pretty straightforward. So we've got a similar but slightly different example. A cart is pulled by a rope at 30 degrees to the horizontal and it's pulled for 20 metres. The tension force in the rope is 60 newtons and we need to find out how much work is done. So again, we'll draw a vector diagram because it helps us visualise what's going on. So we've got a tension force here of 60 newtons and this tension force is acting at 30 degrees to the horizontal. The distance that box is pulled is 20 metres. So we can use our rule, work equals force by displacement. But in this situation, the force is acting at an angle, but we can only use the force that's acting parallel to the direction of motion, which is horizontal. So we need to resolve this vector into its horizontal and vertical components. We don't really need to worry about the vertical component, we just really need to worry about the horizontal. So with our triangles and trigonometry, if this is 30 degrees, we know what the hypotenuse is. We want to find out what is adjacent. We don't really mind about what is opposite for the moment. We'll use cos adjacent over hypotenuse. This will rearrange to adjacent, is equal to hypotenuse cos theta. The A for adjacent is representing our force that is acting horizontal, so the horizontal component of this 60 newtons, which is acting diagonally, and our H is the diagonal force, which is 60 cos, and then 30 degrees. So we can now sub this into our equation here, and we'll get work is equal to 60 cos 30, and then our displacement is 20 metres. If we pop all of this into a calculator, we'll end up with around 1039 joules. This next example is a question where your conceptual understanding comes into play. So a person exerts a vertical force on their briefcase as they hold it. The vertical position of the briefcase remains the same as they walk to the right, so horizontally, for 20 metres. What is the work done on the briefcase? Now, if we were to draw a vector diagram, the force would be acting vertically upwards on the briefcase, and just to throw the distance in, it's moving 20 metres to the right. There's no force acting parallel to the displacement. So our force is acting upwards, but the displacement is horizontal. So we can't resolve this vertical vector into a horizontal and a vertical vector because it's solely vertical. Therefore, there's no work being done on the briefcase. Even though it's moving, because the force is acting on the briefcase vertically, there's no work done. If we wanted to have a go at the equation, work equals force times displacement, we could try and say that work is equal to F and then cos and then 90 degrees. And then we could put in 20 metres for displacement. But if you put cos 90 into your calculator, you'll end up with 0. So work, because this here is 0, the overall work will be 0 joules. So you can do the equations if you want to, but it would be more than adequate to say that because the force is acting vertically and there's no force parallel to the direction of displacement, then the work done is 0. For our last example, we're looking at change in energy. We know that work is equal to change in energy, so it's quite similar. You just have to know that work is equal to change in energy in order to attack these problems. So a pitcher applies a constant force of 14.2 newtons on a baseball over 2.10 meters before releasing it. What is the baseball's change in kinetic energy? So we know that work is equal to change in energy, and work is also equal to force by displacement. Therefore, the change in kinetic energy is equal to the force, which is 14.2 newtons, by the distance, which is 2.10. Therefore, if you pop all of that into your calculator, the change in kinetic energy will be about 29.8 joules. So for those questions, it's pretty much exactly the same. You just have to equate the work with the change in energy.